very much. Thank you, Ralph. Next up, we have Laris from Third Planet Networks talking about network convergence.
Hi, my name is Laris Benkis, and I want to talk today about measuring convergence on IP networks, and specifically on a technique of doing that on production networks. So, the tools that we have available to us today to measure the performance of our networks, implicit in the measurements is the fact that the measurements assume that the network is at steady state. There's no actual way of measuring a network that's changing. If you happen to catch a measurement of when a network's changing, you end up with some sort of strange outlier that you can't really correlate with anything. So there are no tools right now to be able to measure this kind of thing. And you can measure convergence on a network, but it's not something that's easy to do. I can give you a rhetorical question like who knows how fast their networks converge, and if you actually do and have measured it, when's the last time you did it and how often do you do it? The answer is probably not very often, and well, why is that? Because to measure the way, I've done this on some production networks, and the way you do it is, well, we ran packets across the network and caused a failure in the network and sort of counted how many packets were lost, and that gives you a measure of how fast the network responded. So there's like two really obvious problems with that. One is that you're causing a failure in your network, and well, we spend our careers trying to minimize network downtime, and so this kind of goes against the grain of what we usually do. And the other problem is that it's a manual process. You have to set up the packet stream, and somebody has to pull the cable that causes the failure. So it would be great if there was a way to make these kind of measurements in a way that doesn't cause an outage and in a way that could be automated. So, and this is what I'm going to show. And to do that, we start with a technology that you're probably all familiar with is jitter probes. And just to summarize quickly, you have a device, a sender device, which sends out a stream of packets to a responder. The responder gets those packets, just turns them around and sends them back to the sender, and then you can the sender then can calculate latency, two ways or one way, packet loss, and jitter, the variations in the packet spacing. And so some examples of this are the two-way active measurement protocol, RFC 5357, and 6812, Cisco Service Level Assurance Protocol. So you might know that as IPSLA. Cisco just released that just this year as an RFC, so now it's in the public domain. And there are others. Other vendors have their own proprietary probe technologies. So there are a bunch of them. The one that I'm familiar with, the one that I've done all my work with, is actually the Cisco protocol. So what we're going to do is combine the jitter probes with routing protocols to measure the network convergence. We're going to induce a controlled change in the network to be able to measure the response of the network to that change. And it's not service impacting, and it can be automated. So we start with a network running a routing protocol. It doesn't really matter which one. And it could actually be a combination of routing protocols too. And there's a sender device which participates in the routing protocol, and we have a responder. And the responder can participate in the protocol or not, doesn't really matter. So the sender is going to initiate a probe and send it out to the responder, and the responder turns the traffic around and sends it back. Now what we do differently here from a conventional probe measurement is that the sender is going to send the traffic with a source address, call it A, but that address isn't actually routed on the network, so the network can't return the probe packets back to the sender. And they will go somewhere, probably follow the default route and be discarded. And then, so we're running our probe, the packets are being dropped, and then at some time T0, the sender is going to announce a route for A into the network. So that information is now available, but it has to propagate through the network. So you can, I guess, probably see where we're going here with this. So we announce it at T0, and after some time passes and that information is propagated through the network, at some time TC, the network will have converged. And at that point, the network can actually return the packets back to the sender. So sometime after that happens, the first probe, packet N in the probe, will actually arrive back at the sender at some time TA of N. So then you can, write a relation here. The convergence time, which is equal to the actual TC minus T0, is going to be less than the arrival time of packet N minus T0. So what we've established here is an upper bound on the convergence. It's something less than that, but it's not going to be greater than that. So now we have an upper bound on the measurement, and we can also establish a lower bound on that. So if you think about the packet N, when it was sent out by the sender into the network, you can't really say anything about the state of the network. The network may have already converged, the packet was sent out and it came back, or the network may not have been converged, the packet was sent out, the network converged while it was in flight, and it came back. So you don't know about packet N, but the packet previous to that, N minus 1, you can say that, well, the network wasn't converged when you sent it out, because otherwise you would have got it back. So you can use the send time of N minus 1 to establish a lower bound on your convergence. And so those upper and lower bounds then establish a convergence interval. You can measure to a certain amount of resolution. You can't get TC exactly, but you can get an upper and lower bound on it. And the difference between your upper and lower bound is made up of three parameters. The packet interval between the probes, the packet interval of the probes, and that's a constant value, constant-ish. If you look at some of these probe streams, it's not as constant as you would think, but call it constant. The round trip time of the network, and that's something that can vary, but certainly packet to packet you can expect that to be pretty constant. And the last parameter is what I'm calling the responder dwell time. And what that is when a packet comes in to the responder, it may not send it out again right away. Certainly if it's a Cisco, in the Cisco implementation, the responder can be a router, and the router is busy doing other things. Its primary job is to forward packets, not to be a responder. So it may not send the packet back out right away. And Cisco deals with that by timestamping the packet on receipt and then timestamping it again when it sends it out. So you can subtract out the dwell time when you're calculating your latency. And that's great if you're calculating latency, but in this measurement you can't actually subtract it out. So the dwell time serves to artificially raise the upper bound on your convergence. And you'll see an example later of where you see that actually happening. So the technique can be applied to any routing protocol. As I described there, there was no mention of a specific protocol, or you can have multiple protocols, one after another, redistributing into one into another, and it'll still work. And if you have a probe implementation that supports V6, you can do V6 as well as V4. A nice, a really nice feature of this technique is you don't need clock synchronization on the network. All the measurement is actually done on the sender, so there are no issues of synchronizing across the network. And the last one, which is a really important point, is I illustrated a single probe being sent into the network. You can, and in practice it makes more sense, to launch multiple probes to multiple destinations. That way you can get a measure of a whole range of routers in the network responding to a network change. And you can see, you'll see examples later where you can see the impacts of topology and how routers interact with each other, which becomes very interesting. If you're running an MPLS network, you can run these tests through a VPN. The measurement device could be connected to the VRF, to a VRF on a PE, and you can measure convergence of VPNs. And an interesting trick as well is you can announce a BGP route with a particular next hop, and then you launch a probe that uses the address of the BGP route, but you start playing with the convergence of the next hop. And that forces a convergence of a combination of your IGP plus LDP, so you can see how fast your LSPs are being set up. So this technique offers a lot of advantages over the conventional ways of measuring convergence, but you have to be aware of, it's not, there are things that it doesn't do. So if we look here at a model for SPF convergence, there's a bunch of parameters that contribute to a measure of convergence in SPF. Now, and that's failure detection, LSA origination, flooding time, shortest path, the RIB and FIB update, and the line card update. Now, in this technique, the first two parameters aren't actually measured because you're creating like a synthetic network event. There's no real failure. There is no failure, so there is no failure detection. So you're not measuring that. And there is an LSA origination, but it actually originates from the test device, so it's not an attribute of your network, so it's not relevant to how your network is performing. So it only measures part of the whole picture. So you need to be aware of that. So if you use this to measure your network's performance, and you find that you have a SPF convergence of 200 milliseconds, and you think that's great, but if you're relying on 10-second OSPF hellos for your failure detection, then the actual performance is going to be wildly different than what you measured. So, is this useful? I think so. It gives a picture of how your network's working in a way that none of you has probably seen before, and it can be used for SLAs. Certainly you wouldn't publish an SLA for routing convergence to your customers, but it could certainly be useful as an internal network SLA. And you can baseline and track the performance of your network, and and spot when changes to the network may induce changes to routing that aren't readily apparent with the conventional tools that we've had to date. Network architecture validation. So you reorganized your network. You had a full mesh BGP, and then you went to a route reflector architecture. I guess intuitively you understand that well, with a route reflector, there's more hops, so won't be quite as fast as a full mesh. But can you qualify what that means? With this technique, you can, actually. And troubleshooting, network and routing performance. You'll see an example of that. And to me, the speed and how well your network responds to change it's kind of like QoS. You put in QoS in the network, and does it work? Probably, but do you really know? And if you have a failure at one point that could be attributed to QoS, how do you track that down? Once it's in there, you don't really know. And I think the routing performance in some ways is kind of the same thing. And this technique gives you a window into how the routing protocols are working and kind of shed some light on that issue. So to show you this technique in action, we have a small sample network, and it's very important to look at the topology, because you'll see the graphs that you get out of this, how dependent upon topology the measurement of convergence is. So we have the convergence monitor, and directly connected is a router R1, and then we have R1 has 2, 3, and then off of R2 we have R4 and R6. And so you'll see the impact of this topology in the graphs. So this is, call it the bread and butter slide. You can measure all kinds of interesting things, but the first question anybody's going to want to know is, how fast does my IGP converge? Because that's really question number one. So this is a measure of that sample network of SPF convergence, and you can see we start out and we're close to 5 seconds, and suddenly it drops way down. So the left hand, what you see there is vanilla out-of-the-box OSPF, and their convergence is limited by the SPF delay, which is an architectural constant that John Moy specified when he developed the protocol. So that, of course, we can tune now on, we have knobs to adjust that, and that's what you see when you adjust those knobs. You can see the convergence drop off. But the kicker here is that the whole network was already tuned for fast convergence except for R1. And that one router wasn't set properly, and because it was converging slowly, from the point of view of the convergence monitor, the whole network was slow. So like one badly positioned router can spoil the party for everyone. But a tool like this can spot it very easily with no impact to your subscribers. So this is the same graph, but I'm zoomed in on the tuned portion, and we can start to see some of the topology effects. It could be better actually, because the traces are really compressed together. But on the bottom part, R1 converges first, and then there's R2 and R3, and then there's a big jump, and then R4 and R6. So what's going on here? Why do those other two converge much more slowly? They're the ones downstream from R2. And the answer is, I don't really know. When you start getting these kind of graphs, you very quickly find yourself asking very pointed implementation type of questions, like why does a particular router behave in this particular way? And this is an example of that. Everything downstream from R2 is converging appreciably more slowly. So would like to look closer at R2 and see what is going on with that. So fortunately, I can't answer that question, but it's interesting. But the point is, a tool like this lets you ask questions like this. And now, switching to the convergence of external LSAs. Again, we have a very similar pattern. R1 and R2 are converging very quickly, and then R1, R2, and R3. And then the ones downstream from R2 again are up at 220 milliseconds. Again, it points a finger to R2. We can do BGP as well. And on this little network, everything is very fast. The slowest convergence we see is down around 20 milliseconds. But what's interesting here is that topology dependence is broken because the slowest converging router is R2. R4 and R6 are actually converging first. And this is happening because of that dwell time that I alluded to before. R2 is actually holding on to the probe packets longer than the others, and that artificially raises its upper convergence bound. So in all these slides, we see there's something with R2 that's, it may be a fine router, but it's certainly different than the others. And so you can start asking, these are the kind of questions that drive your network, router support engineer bonkers. Like, why is it doing this? And he's going, I don't know. So, having a router be an SLA responder Cisco actually recommends that you don't do that. Certainly for important routers, that you use a shadow router that just sits behind your PE and responds to SLA probes while the PE does what it's supposed to do, which is forward packets and deal with routing changes. So that's it. I hope you found it interesting, and if you have any questions.
I'm a GT with GoDaddy. I'm just curious, the networks you've implemented this in, what kind of trouble did you identify that wasn't being identified with standard practices right now for longer?
I'd love to say that I have deployed this in production networks. I am talking to some service providers, and there's one where they have agreed to promote it to production, but I have not. I have only tested this in laboratory environments. So this is the kind of thing that that I've seen. I can't report, and if I had, I couldn't really discuss what I see on somebody's network. But no, I wish I could respond better to that question, but I can't. I'm sorry.
Any more questions? All right. Thank you very much, Laris.